of course, to capture also the CO2. However, this is very challenging because we are speaking about huge amounts of gas. And now we have only, for example, cannot move forward. We are looking into the coke gas of Eindhoven, one producer of steel in Turkey. They are producing 320 million cubic meters per year of the coke oven gas, and this coke oven gas contains huge amounts of hydrogen and also other burnable components. And this is only one gas stream. There are also other gas streams in the steel industry which are of interest. But however, we looked only on this one. And the idea was the following: we are taking part of the gas, not all, only 10 cubic meters of the gas. And first, we are trying to separate the hydrogen or a part of the hydrogen from the gas by a silicon carbide nitride membrane. And then we are getting a permeate, what contains a high amount of hydrogen. And we are getting a retentate, what is 50% of the initial gas stream, what still contains a lot of caloric components. And therefore, we can use this gas for oxy-combustion process to produce electricity. As this was the initial idea, to make an oxy-combustion. And by doing so, we are getting at the end a high CO2 containing gas. And this CO2 containing gas then can be treated with a polymeric membrane at a low temperature to remove a high amount of the CO2. And then we are getting a gas stream with 98 or higher CO2 purity, and a gas stream only 1 cubic meters left from the initial 10 cubic meters contains 30% of CO2, and we would, by doing this, recover 90% of the CO2. Well, the polymeric membranes are running at low temperature, the ceramic membrane at high temperature. Of course, we are using membranes, it's energy saving and free of chemicals, what is very nice. Well, and now in my presentation, I only will speak about this type of membranes, the silicon carbide and silicon carbide nitride membranes. Well, why using this material? There are also other materials possible, of course. Yes, there are zeolites, they are crystalline, metastable. Some of them, they are high thermal stability, but some of them have limited hydrothermal stability, but it depends on the composition. And it's always challenging to make defect-free membranes from these materials. It's principally possible, but it's challenging. Carbon have very good separation performances, but the stability is limited up to around approximately 400 degrees C. Silica, we all know, have limits in hydrothermal stability, but it can be improved by introduction of carbon. There's palladium, what would be the perfect membrane for hydrogen separation, but we know it's expensive. Needs high application temperature, and there are also certain stability limits. However, silicon carbide and silicon carbide nitride are well known in ceramic industry to be very stable hydrothermal as well as thermal, and so the melting point of silicon carbide is, to give an example, more than 2,700 degrees C, and it's not soluble in any scale. So it's an interesting material, but however, to make membranes of them is also very challenging. Well, we started to make such kind of membranes on top of alumina substrates. We used single channel elements with a final supporting layer of gamma alumina with 5 nanometer pore size. And then we coated these tubes inside with submerged available precursors. You can see here, right hand side, one for the production of silicon carbide, and the other one for the production of silicon carbide. And then we had to cross-link them, and we proceeded in pyrolysis at a separate cell in argon, and by doing so, you should get the ceramic membrane. And we got very nice layers, yeah. Looks very perfect, thickness 150 to 200 millimeters, very, very thin and very, very smooth. And smoothness is, of course, related to the gamma alumina layer that is below. Well, then we made, of course, single gas permeation tests at 300 degrees C. And how you can see, in both cases, we got very high hydrogen permeances in the range of 10 cubic meters per square meter hour and bar, what is equal to 10 to the minus 6 moles per square meter second Pascal. And for both cases, we got the lower permeances for the bigger gases. We got a certain selectivity or ideal selectivity for hydrogen over CO2 in the range of 3.5 to 4.5 for the silicon carbon nitride, what is above Knudsen, and quite nice in the range between 7 and 9 for silicon carbide. So silicon carbide seems to be the most promising membrane for hydrogen CO2 separation. Therefore, we also made mixed gas permeation tests with this kind of membrane. We mixed hydrogen and CO2 50-50, and then we proceeded the test at 300 degrees C. We varied the feed pressure between 2.5 and 5.5 bar. Permeate pressure kept at 1 bar, and we didn't use any sweep. And how you can see in all conditions or in all pressure differences, transmembrane pressure differences, we always got a much higher hydrogen flux than CO2 flux. However, with increasing the pressure difference across the membrane, the hydrogen permeance kept constant, the CO2 permeance increased slightly. And because of this, the selectivity decreased a little bit, but however, the initial value at 1.5 bar pressure difference was quite high, with a value of 10. And then it goes down to 6, but it's still quite okay for our separation task. Yeah, reason for CO2 increasing, we think, is there are still some defects in the membrane. But however, it's a very nice hydrogen selective membrane. Well, then we made a microcharacterization of the material, of the silicon carbide as well as of the silicon carbon nitride. And what we have seen in both cases, we found a lot of oxygen. This was really surprising. And if you're looking into the PDX mapping on the right-hand side, you can see that oxygen is more or less everywhere, while the carbon and the nitride, they are, as a nitrogen, are only on some dots. Yeah. So practically, it seems that it's more or less a silicon membrane with some silicon carbide or silicon carbon nitride dots, and the dots do have a size of 20 to 30 nanometers, very small dots. Yeah, this was a little bit disappointing. However, we made stability tests with this membranes under harsh conditions. Yes, we treated them over 5 days at 300 degrees C and 15 bars in saturated water atmosphere. And surprisingly way, the silicon carbon nitride had been stable. Yeah, we measured the same permeases than before. So in principle, we can use this membrane. It seems that the dots are stabilizing the silica. For silicon carbide, unfortunately, we have got a reduced selectivity. So principally, we can use it only in the absence of water. There's not enough hydrothermal stability. Well, and what is the reason where the oxygen is coming from? And there was the idea made. It's because of the substrate. Yeah, we have a gamma luminal below the membrane, and the oxygen is moving into our membrane. And therefore, we got the idea, well, let's use an oxygen-free substrate, and this could be silicon carbide. And Saint-Gobain is a producer of microfiltration membranes made of silicon carbide. And therefore, they had the task to prepare the substrates by extrusion and then to prepare intermediate layers by slurry coating. And on top of the final layer, we tried to make the polymeric precursor. However, the problem is that the membranes Saint-Gobain is producing up to now, we have quite big pores. Yeah, so also the final layers, and the pores are much too big for coating with a polymer. This is a portfolio of the Saint-Gobain production line. Yeah, they are using recrystallized silicon carbide, and these have a very high purity, and therefore is very chemically stable, and it has quite high permeances because the open porosity is bigger than 40%, what is quite high, and also the pores to have are quite straight. They are preparing membranes in different geometry, mostly as tubes, from single channel tubes to multi-channel tubes of different diameters and a number of channels. And in the bottom line, we can see what is the pore sizes they are able to prepare. And then you can see that the carrier, the substrate, have pore sizes up to 10 microns. And then they have an intermediate layer, and the final membrane layer they are able to produce. This is a range of 250 millimeters. As I mentioned, big pores to coat directly with the polymer. And therefore, they had at first to try to reduce the pore size of the last membrane layer. In the first step, what they have done, they reduced the sintering temperature for the final layer. And by doing so, they made an additional final layer, and then they treated it at a lower temperature. And by doing so, they could reduce the pore size of this layer down to below 100 nanometers, anywhere between 50 and 100 nanometers. Very nice, but it's still not enough. And therefore, they made a second step with a little bit another precursor material. And by doing so, it was really possible to get a membrane layer with a pore size in the range between 30 and 50 nanometers. This is very nice, and this is also quite interesting for Saint-Gobain, because now they have a new kind of membrane that can be used also in liquid filtration. However, we tried to use this substrates for our gas separating membranes. And at first we had to look for the polymers as precursors. And we tested a lot of different polymers, how you can see here, and we tested a lot of different mixtures. Here we have 28 trials, with different mixtures, with catalyst or without catalyst, with solvent or without solvent, etc. However, we see only the last lines of this trials, and these mixtures seem to be the best. The mixture of C4 and C5, you can see here what it is. And with this material, it was really possible, they are commercially available, what is quite nice. And with this materials, it's really possible to form a layer on top of the silicon carbide substrate. How you can see, yes, the surface of this membrane from Saint-Gobain, also the process is quite low, is not very smooth. Well, however, preparation of oxygen-free membranes is challenging. You have always run the work in inert conditions until you have a ceramic material. So we have to make the synthesis of the polymers and coating in a glove box. We have to transfer the coated membranes into the oven in inert conditions, and have also to store the coated membranes in inert conditions before they are sintered. And also during the pyrolysis, we found out that nitrogen 5.0 still contains some oxygen we didn't know before, and so we had to change to argon to. Okay, however, we have done all this and it works more or less. And then we had another problem what we hadn't in mind before. If you are coating membranes inside of a tube, you need an end sealing for the membranes. And however, if you are using the glass, what we are typically using on our aluminum tubes, these glasses are not working on combination with silicon carbide. You are getting such gassing of the glass and bubbles, etc. You cannot use it. And this needs, of course, a lot of time to develop alternatives. And we developed two alternatives: a metal sealing and also a new glass sealing, and both are gas tight, what is very nice. And now we had, for the first time, membranes for doing permeation measurements and also are able to scale up. And I show you as a nearly last slide the very first result of permeation measurements. This result is not great. How you easily can see, here's an example of variation of the coating time. And when we are coating quite short, we have dramatically high permeances in the range of 100 cubic meters, square meters hour and cubic meters, square meters hour and hour. Yeah, and if we are coating for a long time, we are getting a very low permeances, and however, we can also see that the ideal perm selectivity of hydrogen over CO2 is only in the range of Knudsen, 2.2 to 3. And we can also see that the SF6 permeance, the permeance is the biggest molecule, is still quite high, so we have a lot of liquids. Right. Yeah, so all in all, there's a lot to do left. Okay, with this I come to the summary. We try to develop silicon carbide nitride membrane to scale them up and to use them finally for the hydrogen separation of open gas. We got very good results with membranes on top of alumina substrates, especially with the silicon carbide. We got very high selectivities, but also with the silicon carbide nitride, we got very high selectivities. However, in both cases, we got an intercalation of the oxygen into the structure. And so the silicon carbide membrane, what was a resting membrane, was not selected anymore after a hydrothermal treatment test. Therefore, the idea was to run the experiments on non-oxide silicon carbide substrates, and Saint-Gobain developed fine porous intermediate layers, and we developed precursors, and we developed recycled metal and glycan sealings, and now we are testing the permeation properties. And what is the next steps? Well, we have to optimize the coating technology to get dense membranes. We have to scale up to 4.5 meters long elements, and also possibly in multi-channel elements. And our partner in Turkey have to build up the prototype of the pilot unit. What is going forward? This is, I'm at the end. I thank you for your attention.
Thank you very much. Due to our tight schedule, only time for one small question.
Okay, thank you very much for the presentation. You show selectivities of 9, and you mentioned it's very high. Obviously, everything is relative. What is the target of for this selectivity, and in which industry is interesting to have 9 as a?
Yeah, coming from palladium membranes, seems 9 is nearly nothing. But 9 is quite enough for the preparation of a hydrogen of not highest quality. Yeah. When you need only a hydrogen of something more than 90%, what you need, for instance, for reduction processes in steel industry, then it's really quite.
Okay, thank you very much. Yeah, sorry, due to time, we have to move on to the next speaker, but we still have 2 days to discuss during lunch and the social event and the dinner. So save your questions for that. Thank you again. Next speaker of this morning is Dr. Yuri Koleko from the International Iberian Nanotechnology Laboratory, and he is linked to the MEMCAT project and will enlighten us with membrane-assisted ethylene synthesis over nanostructured TEM catalysts. Of course.
Hello, everybody. Good morning. My name is Yuri, and I will speak a little bit about our project, which we are presenting here. Unfortunately, my talk will not be so scientific, so I'm sorry in advance for this. But all the scientists working on the project is around here. If you would like to speak science, we will always connect you to the proper people. So just say about myself a little. I'm originally from Russia. It's not so popular country now, but I'm now working in Braga, which is north of Portugal, very close to Spanish border with Galicia region. And it's a small city and a very beautiful city. And you all invited to go there and see. It's a very nice Catholic city. When you go there, of course, eat bacalhau. And especially with vinho verde. That's what is it. And don't forget for the dessert, take the pastel de nata. And when you go there, try to spend as much money as possible, because it's good for our small country, for our economy to grow. And And in Braga, there was recently built a new institute called International Iberian Nanotechnology Laboratory. This institute is created by the Portuguese government, by Spanish government. So we have international status like CERN, and we work in our mode of operation is kind of like an embassy. And it's celebrating like in operation 15 years old, and since the signature of the memorandum of understanding between two countries, it's like 20 years. Now we are around 600 researchers, and the institute main business, it's a clean room. We have a very nice big clean room, and we work with information and communication technology, life sciences, and we are particularly working with energy and environment. And here is our group, and we investigate unconventional nanomaterials for sustainable chemistry. I would say we are like more like chemistry group, and I think we are very good in cooking. So if you search for the reliable partner for your new European project adventures, here are the people waiting for you. And a little bit about our project, I will speak a little bit about motivation, and then introduce you to our project. And as you know that there are a lot of CO2 emission, it's change of temperature of the Earth. There is some concerns about it. And as you, for example, for 2023, data shows that per year the total emission it's around 41 billion tons of CO2. Most of this comes from the fossil fuels and industries, and also from the land usage. Fortunately, we have ocean next to us and forests, and they can sink around half of these carbon emissions produced in the earth. Roughly 8 billion tons is sink by the land, and then the rest go to the ocean, which is good, but is also not so good because the ocean like this getting more acidic. But still, there is at least in 2023 was 22 billion tons of CO2, which can be used which goes to atmosphere unwanted, and we thought that we can try to do something and use, as was explained by Professor Aresta, use it as a carbon source. And it's expected that carbon capture utilization will grow. Around 700 million tons of CO2 will be captured predicted by 2036. So this technology is in full gas. And then there is, of course, if you use CO2 as a carbon source, you can produce different chemicals and polymers. And so this is a good raw material to work with. And in our project, we are targeting the product is ethylene. And of course, you will say, okay, it's not cool. You are taking CO2, you are doing carbon neutral things, but you produce ethylene, which is mostly converted into the polyethylene, and plastic is not good for our planet as well. But in the same time, ethylene actually contributes a lot into the sustainable movements in the planet. It's very strongly used in the healthcare applications. It's also critical material for the renewable energy installations, such as solar cells and wind turbines. And it's also very good advanced materials for industry, developing materials for construction, automotive. So it's play not only critical role in our, like, for example, food sector, but it's also contributes a lot into the new renewable and societal healthcare technologies. And unfortunately, production of ethylene in Europe is decreasing. And for example, there was a news few months ago, there was a big cracking plant to produce ethylene in the United Kingdom, which was closed. And you can see, for example, in China, and the United States is increasing. And in Europe, why it's closing, because you have a lot of restrictions, and also the fossil fuel stock generate more CO2 emissions. So there is environmental concerns and regulation concerns, which makes production of ethylene in Europe not so favorable. So this essentially means that the shift to new, not fossil fuels like CO2, and the new production pathway, it will be beneficial for the European Commission. And then our approach is we, of course, in laboratory, we use CO2 from the gas bottle and the hydrogen from the gas bottle. But in regional technologies that it will be capturing CO2 and we produce ethylene directly by CO2 hydrogenation. Currently, the most developed technology is bioethanol dehydration, and it's the most commercially mature technology alternative to the naphtha cracking. And a part of this technology, even if it's commercially mature, the more sustainable approach would be to take CO2 and hydrogen and produce ethylene. And by using CO2, we are closing the carbon loop and reducing our dependency on the fossil fuels. And what I would like to say is that closing this loop, taking the renewables and produce the chemical product will be a very good circular economy goal. So to produce directly ethylene from CO2, there is a nice emerging technologies. One is like electrochemical CO2 conversion to ethylene. Another is a two-step way, like you firstly take CO2, you produce methanol by hydrogenation, and then you use methanol to olefin industrial methods to produce olefins. And in our case, we are targeting direct CO2 hydrogenation to ethylene. And our targets, of course, everything high yield, high efficiency, and high selectivity. And for this, we come up with the project with the same idea I was telling, that we use renewable hydrogen captured CO2, and we produce ethylene directly using membrane catalytic reactor. And we are targeting the project to achieve 80% CO2 conversion and around 95% CO2 selectivity. So how we are doing it? We are developing nanostructured tandem catalysts, which are placed in membrane reactor, and we use a composite oxide so light catalyst in order to be able to hydrogenate CO2 and convert, for example, methanol product into the olefins. And then we also trying to understand the mechanistically this process using simulation, DFT simulation, machine learning, and also operando observation, like in situ operando IR and drift and Raman. And also we are working with a catalytic membrane reactor itself to design it for direct conversion of CO2 to ethylene. And also we are preparing, of course, if we speak about membrane separation and membrane reactor, we need to develop very nice and good membranes for this purpose. For this, we assemble partners from around the Europe. We participate in a project is coordinated by ENEL, by us, me, myself, and we have University of Vigo as a partner. They are developing the materials for the selective ethylene absorption and for the membrane preparation. Then we have partners from the Technical University of Eindhoven, Fausto is here, who is dealing with membrane catalytic reactor, and OneCube as a dissemination communication partner. We have a simulation group, which is now giving a talk in parallel room by Carolina from UWSCT University. They are very great scientists with simulation and microkinetic modeling of the catalytic reaction. We have Frieshaven Institute of Catalysis, who is testing the materials, in charge of catalytic testing and operando study. And then we have a partner from Calabria University, who is leading the work package on the membrane development. So we are having like 4 work packages because it's a project old, it's still not lump sum, like new projects nowadays. So we have some processes that to have a good communication, like Ali was telling today within the project. So we have working groups working on catalysis, membranes, and reactor, and we also try to communicate the outputs of the projects and one of these outputs of communication. It's this workshop, for example. This is just no science, but this is how our catalyst looks like. It's composite materials of oxide and cellulite. This is how our membranes looks like. We are working with carbon type of membranes. And this is how our catalytic data looks like. We study direct CO2 conversion to ethylene. For example, here, our initial study shows that we already can produce ethylene. Still, the space-time yield low, but we still have more than 2 years to go. Yeah, and of course, as the project generates some innovation potential, we can develop new catalysts, theoretical descriptions, temperature resistant selective membranes, catalytic membrane reactor itself, and of course, direct process of converting CO2 into the hydrogen. Yeah, so we hope also that our project will achieve long-term impact, enable like carbon negative production of light olefins. Also, ethylene will play a critical role in the green economy and sustainable developments. And hope this new type of technologies will place Europe in good shape for the future challenges in terms of the chemical production from CO2 and from the renewable feedstock. And also, we think that this technology can be also in future extended not only to CO2 to ethylene, but some other application as well. Yeah, and this project also has potential, as we know, because the capture of CO2 technology is keep developing, and the captured CO2 will be just increasing in hydrogen production. Okay, so I hope I was able to convince you that Melcat will harness basic science to catalyze energy transition toward net zero targets. And thank you for your attention.
Thank you. Well, we have time for questions.
Your product, of course, will be a mixture of substances, olefins, olefins, and also longer chains. How do you separate this?
Yeah, so we have a membrane reactor, and first membrane in our case is working as a water selective membrane. So we are removing water to produce more methanol, because methanol in our case is an intermediary. The idea is to bring the CO2 to methanol and methanol to olefins all together in tandem. And then you have the gases passing. Of course, you have a gas mixture, large gas mixture. So we would like to achieve a high selectivity to olefins itself by catalytic process to have less admixtures like CO, like paraffins. And after we will have a separation unit which will be having ethylene selective membrane. So it's not in one pot, it's in two pots.
Kind of membrane?
We work with carbon molecular sieve membranes, which are for water selectivity is reinforced with, not reinforced, but they have additives to make the membranes more hydrophilic. And in case of the ethylene separation, they have metal organic frameworks additive to increase the ethylene selectivity. Thank you.
Questions? Maybe I have a question. So the catalyst is 4-shell catalyst?
Yes, yes.
What is 4? What is shell? Can you?
We are trying both. But current modification is you have methanol catalyst as a core and zeolite catalyst as a shell.
And they are nano, so how small are they?
Well, the zeolite is not so nano. It's difficult to make. The zeolite crystals are like half microns. And this photo I was showing, it's This is quite large scale. It's actually press and sieve fraction between 200 and 350 micrometers. Yeah, but methanol catalyst is like around 10 nanometers.
Then you heat them up to 300 degrees.
Yeah, we go up to 400, but we also, our target is also try to reduce temperatures as much as it possible. But the problem is there that for methanol, for methanol, CO2 to methanol, you need a high pressure reductive atmosphere and let's say low temperature 250. But for MTO, methanol to olefins, you need you should operate in atmospheric pressure, no reductive atmosphere, but high temperature. And by tandem catalyst, we can try to bridge them together.
Thank you. Let's thank the speaker again.
Thank you.
And we move on to a presentation of the chairman of our workshop.
And paparazzi.
Paparazzi, Professor Gauch from Eindhoven University of Technology, and he will explain how these membrane reactors from methanol synthesis work. Floor is yours.
How they look like. Thank you very much, and thank you, the organizer, for inviting me. It was very, very nice. Okay, so I will show you what we do with membranes and membrane reactors in this presentation. A little bit of commercial. Unfortunately, we are in the Netherlands, so I will not put any picture of food. And probably you understood already why. But when I started in Eindhoven, together with Martin Masintananen, that is also sitting here, I started my collaboration with Tecnalia. Tecnalia is an institute in Spain, in the north of Spain, or in the Basque Country to be more precise. And there they have good food, very good food, but also very good membranes. So we started this collaboration a long time ago, developing membranes from very small scale to larger scale as well. So in our group, what we do is combination of reaction separation. Actually, process intensification is quite a large team in Eindhoven. Together with Martin, we have quite a lot of processes where we combine reaction separation, reaction and heat management. In my case, it's more about plasma, but we have also induction heating and so on and so forth. So reaction and separation, membrane reactor is a typical example. You do the separation through the membrane and the reaction in a catalyst. Of course, you can do also catalytic membranes, but it's not the topic, most of the topic that we do in our group. So a few years ago, there was a very nice paper in Nature, which is called The 7 Separation That Will Change the World, which is a very nice paper, especially if you work with membranes. And they show this graph about emissions, and you can see that it's more or less divided in 4 parts, and a big part is in industry. And they calculated that more than 50% is because of separation. And if you take this separation that generally are heat induced or pressure induced, and you change this with membranes, in many cases you can increase the efficiency up to 90%. Not for all, of course. Which means if you increase the efficiency, you decrease the energy that you use, so you decrease the CO2 emissions. That is the trick we want to achieve. And a membrane then is a separation layer that should be selective. And unfortunately, unless I put a picture of a palladium membrane, which is a super selective to hydrogen, but it's not the topic of this talk. So if you take a membrane and then you put a catalyst and you do a reaction close to the membrane, you have a membrane reactor. So you can have several types of membrane reactors. Here you see a classification where the classification depends on the type of catalyst that you use, the type of membranes. You have organic or polymeric membranes, which examples are bioreactor, and then anything else that is of interest for industry, normally used in organic membranes. And then it depends on the transport function. You can have extraction, you can have the membrane to feed something in the reactor, or just contact it. So a membrane reactor will look like this in the picture. a vessel where you have membranes and you have a catalyst. The picture shows here a fluidized bed. That's why the strange shape of the reactor. And there are several examples that show that the membrane reactor would work. In our group, we did a lot of papers together with Martin, but I also like to use this paper as example, also because Professor Violi was my PhD supervisor. So a little bit of commercial, but they show that, for example, for water gas shift, it makes sense to use a membrane reactor, but it doesn't make sense for all the reactions. So you have to have a problem in the reaction itself. And most of the time, it works when you have, for example, equilibrium reactions. When you have equilibrium reaction, you can optimize the catalyst, you can do core shell, you can do whatever you want, but you reach the equilibrium if you fix temperature and pressure. In that case, if you extract a product, then you can shift the equilibrium. Now, what is nice is that all the reactions that involve hydrogen are equilibrium reactions. So either you produce hydrogen or you use hydrogen, then is a typical example where you can use membrane reactors. And one of our PhD students made this very nice picture where you see how in all the possibility where you can use a membrane reactor, whether to take CO2 and hydrogen and form something, up to taking, for example, ammonia and getting back the hydrogen. Now, coming back to the methanol, this nice paper here shows the market of methanol in the last years. So not only for the CO2 valorization is important, but it's a chemical that is very, very important. And in the last years, it's even increasing more steeply. Methanol you can produce, and is produced from several feedstocks. And then as for hydrogen, you have the green methanol, you have the gray methanol, and so on and so forth. So what is interesting for us is whether we start from biomass or whether we start from CO2 to use the CO2 and the hydrogen, or the syngas from the biomass and produce the methanol. Now, as I said before, because methanol production has hydrogen inside, these are the reactions and are typical equilibrium reactions. So are exothermic in total. And you see that you need very high pressure because you proceed with the decrease of volume to get a good equilibrium conversion. Now, if you take a membrane and you start removing water, these are simulation results. Already removing 30 to 40% of the water, you have a much better conversion if you fix the pressure, of course. And if you would be able to remove a lot of water, then the conversion increases quite a lot, which means also that in principle, you could have the same conversion per pass, but working at much lower pressure. Which, if you are working with hydrogen, is very nice because it's easy to get hydrogen from electrolyzer at 30 bar. It's more complicated to go to 100 bar or 120 bar, the typical pressure where the methanol is produced. So how we can separate this water? There are, again, a lot of membranes that you can use. Polymeric membranes, in principle, you could use, but this reaction is exothermic and need at least 200 degrees to kick off, which means most of the polymeric membranes will not survive. But then you have a list of different polymers, different materials, zeolite, MOFs, and so on. And we are working lately with carbon membranes. And in this case, you can decide what to separate. And the easiest one to separate is the water because it's the smallest molecule. So you can do a water selective membrane, remove the water, and get the same effect on the methanol. And this is what I did during my master thesis long time ago when I was black still. And here you see that if you take a conventional reactor and then use a membrane reactor instead of the conventional one, so you have a membrane that separates the water, you can get a boost of conversion. When I present this, the first time was 2020, end of 2020. I was crashed at the conference because they told me, anyway, you cannot produce hydrogen without CO2 because you start from methane. So at that time, there was no much pressure on electrolyzers to produce a lot of hydrogen. Anyway, what is the catch in this figure is that here I was using zeolite membranes. And the results are very nice. What is not shown in this presentation, and I connect to the panel discussions, that to get these results, I got 98 membranes, of which 3 membranes were water selective, of which 1 broke when I tried to put the catalyst inside. So we had only 2 membranes that were working properly. And Hannes is smiling because after my master, I went for some times in Germany. And there was a very nice young Hannes, he's also nice now, by the way, that showed how to produce zeolite membranes, zeolite membrane. And he produced a very nice zeolite membrane that again was not water selective at the end. So I said, okay, I think I should do something else. So I continued with my PhD, taking methanol and producing hydrogen. Anyway, lately we start to produce membranes that you can reproduce with a certain selectivity. And here you see results of a carbon membrane selected to water. Again, this carbon membrane produced together with technalium. And we can reproduce. Of course, the selectivity that we found here, you can do the calculation yourself, are not as big as the selectivity that I was achieving with the zeolite membrane, but it's much reproducible. So if you would have a selectivity that is 100% for water, then you get a single pass increase of conversion, and you don't need to do much more. If you have a selectivity that is lower, then what kicks in is the reactor design. You can still get better conversion. And here are the results. You see that a membrane reactor compared to a conventional one has an increase of conversion per pass quite remarkable. So here you see other experiments where there is the equilibrium. You see that the catalyst is quite good, because in a packed bed we reach the equilibrium, and in the packed bed membrane reactor we go well beyond the equilibrium. Of course, it's the equilibrium for the conventional reactor. Because once I brought a proposal and I was crushed because they told me that I cannot go beyond the equilibrium. So this equilibrium is only for the conventional reactor. Now, what we did here is producing methanol in small reactors, TRL3, closer to 4. Okay, so we are speaking about membranes of around 15 centimeters. So what is next, and this also will be part of the biomega fuel project, is to take this membrane and scale. So in this project, Gaetano is working on the scale up of these membranes, and we will be testing the reactor at TRL5. So compared to the previous experiments, we want membrane of at least 30 to 40 centimeters and many membranes inside the reactor. Of course, what is important is to calculate the cost of the methanol. Also, in that paper that I showed you before, one of the conclusions was that whatever new technology you do, at the end you have to do, or even at the beginning, you have to do a techno-economic analysis, because you can have the best membrane or the best catalyst, but if the financial viability is not there, then doesn't make any sense to continue. So techno-economics is what we are going to do. And then you have to do the design, especially because if you think about biomass or waste gasification, or even if you think about hydrogen production from electrolyzers, this will be always small scale. It doesn't make sense to collect the CO2 and transport the CO2 or transport the hydrogen where you have the CO2. And it doesn't make sense to collect the biomass, at least not beyond a few kilometers in the region. So it doesn't make sense to go in Thailand to get the biomass. For the project, yes, but if you calculate then the viability, I'm sure that you did, and it's not there anymore. And of course, the scale up of the system. So again, this picture resonates with the questions. We want to go from TRL3, where we are now, to TRL 6, 7, and I'm less negative compared to what was said before, because we need support from the European Commission, but we need also to put ourselves in the place. So that's why we just started with Zephyra, which is one of the companies that will take this technology and scale up. And if you look at the techno-economics as well, we also created a company that does calculation, very detailed calculation of membranes and membrane reactors, because you know, when you do the techno-economic analysis, it's always difficult to put these new technologies in. So the company is called Modelta, and today there is also a presentation, or tomorrow, there is also a presentation on the models that they develop and they are putting on the cloud for all the people to use. And with this, I think I have time for some questions. Thank you very much. I couldn't make also the selfie when I was speaking because I had the pointer, but go.
Questions?
Hi, thank you for the presentation. I'm Roberta Racmoni from Guglielmo Marconi University of Rome. It's just like a comment and a push forward, because I'm finalizing my PhD and more specialized in integrating power to gas, so especially producing hydrogen and making stuff work. One of the problems that we're experiencing in Italy, but more or less also in Europe, is the use of hydrogen. Okay, for sure the technology as already at TRL high. The problem is that what we are going to do with this hydrogen. And one of the problems that I see is that all this technology that we are presenting have definitely the word TRL. So one of the things that we want to do was the integration of this hydrogen. We have hydrogen palette in Civitavecchia, 4 megawatt of electrolyzer. What to do with this hydrogen? And one of the possibilities, since we are also close to port area, is producing e-fuels. But if we have already high TRL hydrogen but low TRL with this technology, yes, the scaling up is definitely something that we need to work on, because we need this kind of technology for hydrogen development. So yes, this is the point. Let's continue working on this, because we need our hydrogen.
Thank you very much. And as I showed before, we just started with the company to do the scale up. So if there is any possibility to show the technology that we have outside the labs, we are happy to do. So we are just happy to bring the reactors, even if they are not huge, to place to show that it works also outside the lab. Yeah, there is a question.
I have one additional comment to add. At the beginning of this session, we see some price evaluation of hydrogen produced from electrolysis. They are not wrong in theory, but you need also to consider that value of market of hydrogen produced from electrolysis is higher when you're able to sell it all. So hydrogen in car and in mobility has a higher value compared to the hydrogen that they use in this kind of processes. And if you combine both of them, in the end, cost of hydrogen for electrolysis could be as low as €1 or a couple of euros, and could still be competitive. So that's the point.
Yeah, sure. I mean, we need breakthrough technologies to show that makes sense. Of course, we will never ever reach methanol price as starting from carbon in China. So from in China. So that's we have to take into account, because polluting is very cheap. So whatever we do, we have to take also we have to take also that into account, and also life cycles calculation showing all the footprint are important in this respect.
So, but I understand that techno-economic analysis still has to be done. Can you? How far are we? Is it 10%, 50%?
The point is that you have to be fair as well when you do the technical analysis. So what we are doing at the moment is especially to check the difference between the new technology and the conventional technology starting from the same feedstock. In that case, we are better. But if you take the feedstock itself, so if you take the hydrogen and you put the hydrogen cost at €8 per kilogram, like we do in many techno-economic, then it doesn't make sense. It will be even 2 times more expensive than the methanol as in the market now.
Hi, thanks for the presentation. My name is Kostas Athanasiou. We participate in this workshop in project that tries to do something like this. We have something from chemical membranes to remove the oxygen so that we reduce the water produced by the hydrogenation of carbon dioxide to improve the conversion. What we're not familiar with is this type of membranes that were using in the previous presentation also that are selective in permitting just steel and not hydrogen, that is a very small molecule. Can you give us some sort of insight? There is an introduction and probably we can discuss it outside.
Yes, sorry. Absolutely. Water is smaller than hydrogen as a molecule. So in principle, yes. So water is smaller than hydrogen. So in principle, if you would be able to use a zeolite membrane, which has very defined hydrogen. Yes, it's smaller. Many people don't realize ammonia is smaller than hydrogen. Hydrogen. That molecule. Yes, that simple molecule has a kinetic diameter that is bigger than water. So in principle, it's relatively simple if you do pore size that are all the same and are between the hydrogen and the water. And this would be possible with zeolite, with particulate zeolite, would be possible if you don't have defects, as Hannes showed. So there we have a problem of defects. In the carbon membranes, we have a problem that the pore size is not all the same. So we can restrict the pore size distribution, and we can be close to hydrogen and water, but it's not exactly the same. So there, what we do, we make sure that the pores are hydrophilic. So the water kind of condense, because we are still speaking about very small pores. So I'm not sure if we have to say condense, but hydrogen sticks to the pore, water sticks to the pore and prevents a little bit more the hydrogen to pass through. So it's easy. We reach selectivity that are not 100%, but we have selectivity of 10, 15, in some cases 40. The last results of the MEMCAT project, we show that we can have a selectivity of 40. In that case, of course, you have some hydrogen that may go through. And then that's why I say you have to work a little bit on the reactor design, playing with this with gas as well. But yes, water is smaller than hydrogen.
Okay. I see very nice discussions
Coming
popping
up
up for during lunch. Yeah. So let's thank the speaker again. Then we move on to the fourth presentation of this session, which is from Dr. Vincenzo Vigna. CNR ETM, which is a very long title. So, machine learning based insights into the structure property relationship for permeability and selectivity in gas separation membranes. Thank you.
Good morning, everyone. I'm Vincenzo from ITM, and today with this presentation, I want to show some results that I achieved applying machine learning, artificial intelligence tool, on membrane side, basically. So we start from the main problem, the main objective, which is to build a system that can selectively capture the carbon dioxide from the atmosphere and to reduce the concentration of carbon dioxide in the atmosphere. And we can do this in a very different way, but in this case, we focus on the polymeric membrane to do this. And so what we want to do. Here you can see gas flux. The atmosphere is very complex, but here we can modelize it like only composed by the most principal gas like carbon dioxide, nitrogen, which is the most abundant one, and nitrogen. And so we can see here there are three membrane. The first one is we show high permeability and low selectivity. So the gas can pass through the membrane, but there's no real separation because all gases can pass through it. And we have a membrane with high selectivity but low permeability, so it can act like a filter, but the permeability is low, so we don't have a huge amount of molecule that can separate. So in this scenario, the best one is the one on the right with high permeability and high selectivity. So a lot of gas can pass through the membrane and selectivity. So only the gas we want. And for this, for a membrane, we can define two properties. So permeability, which indicates the amount of the gas that can pass through it, and the selectivity, which is defined toward a couple of gases. So we do the ratio of the permeability. For example, we focus on the nitrogen, and we can define the carbon dioxide nitrogen permeability. So if we put them for each membrane in a logarithmic scale scatter plot, you can see here on the x-axis the permeability and the selectivity on the y-axis. And we can see that organic polymers clusterize in a region, which is not very interesting because we are interested in the one highlighted in green because they show high selectivity and high permeability at the same time. And you can see that there are some trade-off curves because usually when you modify the membrane structure to increase the permeability, you have a decrease in selectivity and vice versa. So each year that are indicated, the trade-off are defined by the most promising materials. And so we have a lot of data of permeability for the polymers, and you can use them to train a machine learning model and use the information from the machine learning model to discover, for example, new material and predict the properties before synthesize them and test them to discover new material with the desired combination of properties. But the problem is artificial intelligence is the big data science. So do we have enough data? Not, but yes, in the sense that we can collect from literature, but they can be dishomogeneous. So we have to collect them and they have to be homogeneous. For example, here you have an example of a data set. So each row is a membrane. Each column is the permeability toward the gases of this membrane. And we have, for example, other properties like temperature and pressure of the experiment. And here you can see that there are missing values because some study doesn't test the permeability for every gas. So I said we focus on the carbon dioxide and nitrogen, but we need the information for other gas too. Why? Because artificial intelligence can help us with an algorithm that is called imputation. So it looks at the complete row, so where we have all the information for a membrane, and it apply the same rule to the missing value. So we input them and we obtain a complete data set. Now we have virtual data, they are calculated, they are not experimental, but at least we have data. And we test this imputation and the performance, the metric performance are very well. We can see that for carbon dioxide and nitrogen, we have hardware, which is close to 1, and it is very close to 1. You can see here from the scatter plot that the green dot, so the imputed membrane, they scatter same as the not imputed them. So the imputation is very reliable. And at this point, we have 1,200 polymer data. The next step was to connect the permeability information to the structure because we want to predict the permeability of the membrane starting from the structure. So the step to make the structure readable for a computer was to move from the repeating unit of the polymer to the saturated monomer, saturated form of the monomer, and then encode them in something that we call fingerprint or molecular descriptor. So basically, with this representation, a polymer is nothing else but something like a barcode. Each one is a functional group that is present. Each zero is a functional group that is not present in the molecule. And then we can, in this way, describe a polymer structure to a computer. And we can connect the chemical structure barcode to the properties that we want. So the model can look at them and learn, the AI, learn the relationship between the structure of the monomer and the permeability and selectivity of the polymer. So I tried different machine learning model. We have linear model, tree-based model, and neural network. But with the benchmark, we discovered that the best one is the extreme gradient boosting regression, which is a very good model because it's very fast. And here you can see the performance metric, which are good. So we build and train a machine learning model, which is quite good in predict with some limitation, the permeability and the selectivity for the polymeric membrane. But when the model is trained, we have to check if it learns something that has chemical science, chemical meaning, and not only mathematical operation. So we move from the explainable artificial intelligence. So the more the model works, but why? So because we have the input, the chemical structure of the polymer, we have the output, the selectivity and the permeability, but what is happening in the middle? What the model is looking at to do the prediction, which is important in the chemical structure of the polymer that we can modify to tune the permeability as we want. And so just to give you an example, we discovered that something that we already know, but now we confirm that the model is looking at something that has a chemical meaning. For example, for carbon dioxide is looking at this Key4N, which is an index of the ramification of the polymer, is looking at the double bond. For the nitrogen is looking at the methyl group. So with this, what we call feature importance analysis, we can look at the structure of the polymer and know what the model is looking at to do the prediction. And for example, one of the approaches is to take one promising a polymer that is close to our upper bond, modify the structure with, for example, function group. For example, we know that we have improved the ramification, something like this, from feature importance, and then propose and predict the permeability for another polymer, hoping they overcome the upper bond. We submit the manuscript of this work, and the Journal of Membrane Science is currently under revision. And now we are moving to the next step, which is not to try to modify the structure, but use a generative model, generative AI model, to generate new structure. And this model can generate new structure, give the structure to our model that predicts the permeability and selectivity, and the prediction model that can give a feedback from a generation to a generative model and give some information. For example, okay, this is not good, move to another direction, and hopefully discover a new polymer structure that can overcome the upper bond. So, in conclusion, we develop a machine learning model that can predict for polymeric membrane the permeability of carbon dioxide and selectivity of nitrogen. We applied some explainable AI tool to understand how it works better. And we are applying a generation prediction approach to try to discover new promising candidates. The next step, we are working on it, are to include the filter. So, for example, MOF for mixed matrix membrane, other characteristic, like, for example, the evaluation of solubility or polymer field compatibility. And another problem is to include the effect of the aging of the polymers, like films, and the temperature in more detail. So thank you for your attention.
Thank you. I hope your generative model also asks his questions very nicely, as ChatGPT does, very friendly and
No, it only generates molecules. It's very, very
questions.
Hello, nice presentation, thanks. There's, of course, permeability and selectivity is one thing, but there is also, you could have a material, a polymer, that works very good in selectivity, permeability, but is not so stable. How is this, are you taking this into account?
Okay, now we didn't take into account until now because yes, there's a problem of stability, for example, for pills. With aging, the permeability decreases very much. So we are trying to include, like, for example, a time series analysis. So we predict how the permeability changes for the polymer during time. So we are trying to introduce other things, not only the permeability and selectivity, but other things to take into account.
Very nice presentation, thank you. I would like to ask, you are using like chemical structure to change the membranes.
Yes.
Is there any other means a part of chemical structure which could bring you into this commercial area?
Yes, you are talking about the generative. Okay, there's a way to describe a chemical structure which is SMILE. So you describe a chemical structure like a string, like a word. So the generative model works like ChatGPT. Instead of generating word, generate the string that is converted to a chemical structure.
A part of chemical structure, can you use something else?
So?
Something else? Like, I don't know, synthesis method?
Yes, maybe.
Thickness?
Maybe, yes.
I forget because I think you are speaking two different things. Thanks a lot, and also Foco from IWSCT. I think we're speaking two different things because Vincent is more focusing on the machine learning part, while you are talking about making the real membrane. So actually, if you see the Robson plot, of course, the target area that it was showing, it actually normalized the permeability at 1 micron thickness of a membrane. But you can, of course, have a very selective membranes with low permeability, but decreasing the thickness going sub-micrometer things, you can increase the permeance, that is the real value that you need a membrane. So actually, there is a trade-off between the permeability, that is a characteristic of the material, and the permeance, that is the characteristic of the membrane itself. So I think you are right. I mean, if you want to push, you can decrease the thickness of the selective layer. Actually, that's what we do in the same projects by doing thin film composite materials. But the focus here on this part of the project is more on trying to understand how the chemical structure can change the polymers and how we can predict material with better performance. Because of course, if you want to have a defective layer, you need to have at least some nanometer thickness. So you cannot go down. There are some intrinsic values that you cannot go down.
Other questions? And let's go to the speaker again. Thank you. Go to the last presentation of this session, which is given by Oriol González Prats. Thanks, Oriol. From Barcelona. He will explain, present CO2 capture and electrolyte materials based on task-specific ionic liquids.
So thank you so much. I'm Oriol González. I'm a PhD student in the University of Barcelona. And today I will present a little bit completed project and my work in this project. So over the last 15 years, the demand of agricultural fertilizers has not stopped growing. And the prediction for the coming years is that this demand will still growing. So nowadays, the method that we have to obtain these fertilizers, like Haber-Bosch for ammonia production or the Bosch-Maser for urea production, has really good benefits, like the reduced cost, the high agricultural productivity, and the practical application. So it's easy to produce, to transport, and to store. However, they have a huge ecological impact. So we need to spend around 2% of the global energy supply to produce these fertilizers. And they are fossil fuel dependent. And finally, we have a problem with the massive CO2 emissions. So on Confetti project, we are trying to develop a new method for urea and ammonia production, reducing this environmental impact. So here you have the general scheme of our project that consists in two different parts. The first part is capturing the CO2 and the nitrogen from the environment, and then using an electrochemical reactor that is powered by electricity, convert into urea. Then, the excess of nitrates that the plants doesn't use, we want to convert into ammonia using a photochemical reactor that is powered by solar energy. So my work, it's on the first part of this cycle that I'm trying to develop new membranes for CO2 capture and activation. So these new materials that we are trying to develop should be solid material, should be stable electrochemically and thermally, should be conductive because at the end we want to use in the electrochemical reactor as electrodes or electrolyte, and finally it should have high CO2 affinity because we'll be the ones in charge of the CO2 capture. So we thought that a good approach was to use ionic liquid-based membranes to develop this material. But let me explain why ionic liquid are particularly interesting for this application. So commercial ionic liquid has excellent properties like high ionic conductivity, negligible vapor pressure, high thermal stability, and they are non-flammable. However, they have a critical limitation. The low CO2 capture at direct air capture conditions. So here is where task-specific ionic liquid appears. So this ionic liquid has a high CO2 capture capacity because they are specifically designed to blind chemically the CO2. However, the drawback of this material is that when they capture the CO2, the viscosity increases dramatically, as you can see in this image, that they become solids. And finally, here is where a practical cycle ion-based ionic liquid come in, that this ionic liquid has the best of both worlds. So they can capture the CO2 in an efficient way because they can blind the CO2 forming carbonate or in presence of water forming the bicarbonate. They have a low energy for the CO2 desorption and the viscosity remains constant after capturing the CO2. So on this work, we developed the synthesis in ionic liquids, that is the resulting combination of these 3 cations and these 5 anions, using a simple 2-step synthesis that we start from the phosphorium bromide that we convert into a phosphorium hydroxide using an ion exchange regime, and then using the neutralization reaction with the corresponding protonated form of the anion, we obtain the ionic liquid in a really high yields. So for the anions, all are commercially available in the protonated form. And in the case of the cation, these two we need to synthesize using starting from the derivative phosphine. Once we obtain these materials, the first thing we did was to measure the capture capacity using thermogravimetrical analysis. Here I put an example of how I perform these studies. So we apply a flux of CO2, or if we want to measure the direct air capture conditions of simple air, dry air, at 30 degrees, and then for the desorption, we heat it until 60 degrees in a nitrogen atmosphere. So the result the capture capacity of the 15 ionic liquid up here in milligrams of CO2 per gram of membrane, and here you can observe the time of pulse saturation of these materials. You can observe that there is significant variations in the capture capacity between the ions and between the cations. For example, in this blue imidazolate derivative shows the worst results. And this was due to the electron withdrawing effect of this R group, that is the nitro group. So we decided to discard it. Another observation was that the parallelate and the benzoimidazolate has the higher capture in all the three different families. And in the case of the cation, the smaller is the cation, the higher is the capture. And this was due to the reduced molecular weight. That means that we can pack more active ions per gram of membrane of material. So beyond the CO2 capture, we also analyze electrochemical characterization, but because at the end we want to use as electrodes or electrolytes. So we measure the electrochemical cathodic window using cyclical tamperometry and the conductivity using electrochemical impedance spectroscopy. In the case of the conductivity, the smaller is the cation, the higher is the conductivity. And in the case of the electrochemical cathodic window, most of the ionic liquid shows an adequate cathodic stability from -2 to -2.7 volts. That is enough for the CO2 reduction, except these ones, the purple ones, that show a smaller electrochemical window. And this was due to a presence of a nitro group in the structure, and we are observing the reduction of this nitro group. So at this point, we decided to use these two anions and the corresponding three cations, so a total of 6 ionic liquid, for the future immobilization in a solid support. To do that, we developed a different approach. The first one that is introduce this ionic liquid inside a polymeric matrix, and the second approach was implement a porous carbon paper with the ionic liquid to obtain capturing electrodes. So if we move to the first approach, we decided to use the simple procedure that is dissolving some polymer in an organic solvent, mixing with the ionic liquid, and then casting it in plates and let the solvent evaporate. In this approach, we tried several polymers, but we were not able to obtain membranes with good physical properties or without having the decomposition of the ionic liquid, or as you can see here, having stability problems, where you can observe that the ionic liquid leaks from the polymer matrix. So we decided to move to another strategy that was use the double network in the shells. To obtain these materials, we used different photopolymerization. The first with this ionizable monomer to increase the affinity between the polymer and the ionic liquid, and a second photopolymerization with the acrylamide to increase the physical properties. Then, after some solvent exchange, we can achieve a 90% of loading of the ionic liquid inside the material. For all the materials, we test the capture capacity into different scenarios in a 100% atmosphere of CO2 and at these C conditions. As you can observe, in a 100% atmosphere of CO2, we achieve a really high capture, around 100 milligrams per gram in one of the ionic liquid. That this is excellent for a high concentration scenarios. However, when we move to a DAC conditions, this capture drops significantly with a maximum of 2 milligrams per gram. In our project, in Confetti project, we have an initial requirement about 5 to 10 milligrams per gram. So with these materials, it's really low compared with our target. So observing this polymer ionoshells limitation, we decided to move to the second approach, that was to use the carbon paper as a solid support. So the procedure is really simple. It's just implement the carbon paper in the ionic liquid for 24 hours and then remove the excess, achieving a loading of 50% of ionic liquid. So here we put two different images. The first of the carbon paper without the ionic liquid, where you can observe the porosity of the material, and the second one after the impregnation, when you can observe that all the pores are filled with ionic liquid. When we test these materials, we saw that in a 100% atmosphere of CO2, the capture was quite the same for all the ionic liquids, between 30 and 50 milligrams per gram. But for me, the most surprising of these results was the time of pulse saturation, that in all the cases is around 1 minute. So this fast kinetics suggests an excellent accessibility of the CO2 to the active size of the ionic liquid. But more important was when we test the results at the EC conditions, that for one of the ionic liquid, we were able to achieve a capture of 15 milligrams per gram, that this exceeds our initial requirements. And it was the first time that we get this high value of capture in IWC conditions. Unfortunately, with these materials, we had problems with the stability. So depend on the surface where this material takes place. For example, you have here an example of an absorbed surface. It's a cellulose paper. We can observe the leakage of the ionic liquid from the material. So the porosity of the carbon paper helps in the CO2 accessibility to the ionic liquid, but it cannot retain the ionic liquid inside. So to solve this, we decided to introduce a third approach. So the idea of this approach was to keep the physical chemical properties of the previous material, but avoiding the ionic liquid leakage. To do that, we just dissolve polymethyl methacrylate on acetone, we mix with the ionic liquid, and we put in a beaker with the carbon paper, and we let the solvent evaporate, achieving a 40% of ionic liquid loading. So the idea was to form this polymeric matrix inside the porosity of the material. So with this technique, we just were able to obtain 4 of the 6 materials in the previous one, because with this one of the pyrrolate, and we were not able to form the membranes without reducing the amount of ionic liquid in the material. For the other 4 materials, we obtained similar results that the previous one, the carbon paper one, and instead in the DEC conditions, that we achieve a maximum of 16 milligrams per gram. But the important thing of these materials is that with this polymer lipid system, we can avoid the ionic liquid leakage. So just as a summary, here I put all the materials that we developed, the 3 different types of materials with the 6 ionic liquid, and we can see that we achieve 2 different materials with higher captures at DEC that it's on our conflicting requirements. And for the future application, we test also the conductivity of these materials to see if we can use as electrodes or electrolytes. And the one that you can see is that the ones that has the carbon paper has the higher conductivities, and when we introduce some type of polymers, this conductivity is reduced. So as a conclusion, we developed the synthetic 15 ionic liquids. We test the capture capacity and the electrochemical behavior, properties. Then we immobilized in 3 different solid supports, obtaining 2 different materials with 1 ionic liquid with high capture capacity in these DEC conditions. So now as a future work, we want to study the permeability of these materials, the CO2 permeability, the long-term stability, and finally the possible integration in some electrochemical applications. So thank you all of you.
Questions?
Thank you very much for the presentation. How do you define the loading of the ionic liquids? Is just weight on weight of membrane?
Yeah, it's by weight.
Okay, and does the ionic liquid stays there in the pores because you show that the pores are covered, or you have a leakage of these ionic liquids?
Depends on the material. So we test the liquid just putting on different surface and observing if it's wet or completely dry. And with this material, with the first and the last one, we can observe that it's completely inside the material. But for the carbon paper, it's you observe that it is wet everywhere. So just. But for the others,
it stays there.
Yeah, for the others, the ionic liquid stays inside the solid support.
I'm Sonia Kerner from Northern University. I have a question. In your project, will you look at the role of the carbon in the support in helping to improve the reaction that you're targeting?
At this moment, we didn't test, so it's a good thing to test.
Thanks for your presentation. Really nice. I'm Zhimian from Delft University of Technology in Iconic project. I'm just wondering, for your technology using the ionic liquid for DAC, I'm just wondering, like, have you estimated the energy consumption for this technology, and what's the advantage compared with like absorption or other general DAC technology?
So we didn't test it. This I thought that the wood part of the ionic liquid is that they can chemically blind the CO2 in this 1-to-1 ratio. So here I put the captures in milligrams per gram, but if you test in moles of CO2 per mole of ionic liquid, you can see that we are more or less about 1-to-1. So this is the good part of this type of materials.
I have different lunch.
No, it was too slow. I have a question. You have a champion ionic liquid, but maybe I miss why this material, why this ionic liquid is the best.
This is a question that we have in the group because we don't know why. We just test, and for this material, we had more or less the same capture in the ionic liquid, and we don't know why when we introduce this material in a solid support, is there is this significant change between the capture in the ionic liquid and in the material, and this is a thing that we don't have the answer.
But you did some spectroscopy or something like this to see if anything like chemically change or.
We didn't perform some spectroscopy. We performed spectroscopy to see if we have the material inside. And at the beginning, that we had these decomposition polymers, we try to extract or dissolve and then go to NMR to see if the structure of the ionic liquid remains the same. But we didn't test. Well, we test with the CO2 to see how is the mechanism, but just with the ionic liquid, not in the materials. But yeah, we need to do it.
When you do CO2 capture, you do it in humid environment or
In
humid.
the thing is that
CO2.
so with this material we have this double mechanism to capture the CO2, and to be constant and to have the same results, we analyze in a wet situation. So we let in the vacuum oven, and then with the TGI we do a pre-test to remove the water, just to keep the same results, because the problem of the water is that these materials can capture water also. So we don't know how to do this experiment in the same conditions for all the materials. So we decided just to do it without water.
Thank you.
Thank you. More questions? There are one more that divides us between these presentations and the lunch.
I'm Salvatore Cannone from Polytechnic of Turin, and I also worked on ionic liquids and the synthesization of membranes. I want to learn about bad results. For example, we have tested ionic liquids with the PIM membrane polymer, and the performance of this membrane was very good in a microbalance. But when we have synthesized the membrane of, I don't know, 5 centimeter, 12 centimeter, and test it in a perimeter applying a driving the pressure, the membrane cracked every time. So did you have seen the same problem? So the fracture of the polymer membrane with ionic liquids or not?
So the thing is that we just perform these membranes in a 1 per 1 centimeter square. So now we wanted to scale up just for the permeability studies. We scale up. We achieve a 4 per 4 centimeters square, but we don't know what will happen when we scale up this procedure. So our idea is now to try to get big membranes to introduce in electrochemical applications, and we hope that this membrane will keep, but we have no idea.
Sorry again, but I think I can answer because you're working with Sergio Bocchini, right? Yes. I tested both membranes. We tested another group, and actually they have the same problem because Gonzalo sent us your membranes, and we are getting the same problem that he's speaking about. So they are not really stable in the perimeter when you put the pressure there.
Okay, I think it's a perfect closure of this session. So let's thank the speaker again. And with that, I will close the session, and I think it's time for lunch, I guess.
Yes, thank you very much also to the chairman. It's okay. So now it's time for lunch. In the other room, there were some technical issues, so probably that will be a little bit late or food for us, perhaps. So we have lunch for 1 hour, and then again we start here with the plenary lecture 2.